All right, let's just wrap up a summary of intermolecular forces that we saw. Dispersion forces exist in everything. They are the weakest of the intermolecular forces. They're present in everything because everything has electrons that can get polarizable, right, and can move around. Polar molecules have dipole-dipole attractive forces. Those are stronger than dispersion forces, and they are permanent dipoles in the molecules. So they're not fleeting, they're stronger. Hydrogen bonding is a type of dipole-dipole interaction. It's just what I like to call a super dipole. It's super special because it's when a hydrogen is bonded to either oxygen, nitrogen, or fluorine, that creates a super polar covalent bond. And then that can have the strongest intermolecular force of attraction that we know. Ion dipole attractions are present in mixtures of ionic compounds with polar molecules. It is a very, very strong intermolecular force, but it's the strongest if we consider mixtures. If we're only considering pure substances, hydrogen bonding is the strongest IMF that we have. Ion dipole forces, though, are extremely important when we start talking about mixtures and aqueous solutions, specifically with those ionic compounds in things like water. So we'll get back to them and we'll give them their moment to shine a little bit later. Nice chart in your textbook if you're wanting to see the interaction. Notice how all of these molecular perspectives have at least two molecules drawn. All right, intermolecular forces of attraction, you need to have the ability to draw two molecules. All right, you can't just do it with one. That's a covalent bond. We're going to be showing it with specifically two. Now, we can see the strength over here on the right-hand side. Strength increases as we get the stronger polarity and the stronger attraction. So what does that mean? That you would, in order to overcome an ion dipole force, we would need to provide somewhere, depending on which one it was, between 30 and 100 kilojoules per mole in order to overcome that intermolecular force. We're going to talk about a few more types of physical properties that correlate, again, with the intermolecular forces of attraction. Surface tension is the first one. We've talked a lot about boiling point, right? But now we're going to see other types of physical properties. Surface tension is a property of liquids that results in the tendency of the liquids to minimize their surface area. That's pretty convoluted, so let's talk about what that means. The shape of a liquid when it is free form, right? Just kind of throw it on a bench or on a tabletop if you're just in your own home. The shape that solution or that substance takes is dependent on how are the molecules interacting with each other. So let's take water, for example. Everyone just go grab a little bit of water, dip their fingers in it, and drip some water on a table. Are you doing it? Pause the video. What happens when you drip water on the table? Well, it bubbles up, right? It creates a spherical shape. Remember, we talked about the spherical surface area as being smaller surface area than a rectangle. So bubbled surface area of a bunch of water molecules, I'm going to try to draw a couple in here, is because these have hydrogen bonding, the strongest intermolecular force. That bubble, that spherical shape, is the smallest surface area. If you have pure acetone in your house, don't go dip your fingers in it. That's probably not a smart idea. Pure acetone can absorb into your skin, dry it out. That's not fun. Don't use the stuff that you have in nail polish remover. It's not that strong of acetone. But if you were to drop acetone on the table, acetone usually would appear as very, very thin sheets, like it spreads out really rapidly. Remember, acetone was this shape, right? It had a polarity, but it's not hydrogen bonding. This has dipole-dipole interactions where hydrogen bonding exists in water. And so the shape, the surface tension is going to be directly correlated with the shape or with the intermolecular forces, okay? So water has a very high surface tension. It holds itself together really tight like a sphere so that the surface area is minimized. So that surface tension, that bubbled up property is accounted by intermolecular forces. Water has 72.8 millijoules per meter squared, all right? Amount of energy required to increase the surface area by a meter square is 72.8 millijoules at room temperature. So what does that mean? It is, if we compare it to another number like C6H6, that's a hydrocarbon. It only has carbons and hydrogens, and we know that is a non-polar molecule. That non-polar molecule tells us that it would at best, right, only have dispersion forces, London dispersion forces, van der Waals. Water is a superpolar molecule. It has H bonding. Now we can compare these two numbers, okay? Looking at C6H6, which is benzene. Benzene has 28 millijoules. Slower surface tension because of lower intermolecular forces, okay? Factors affecting the surface tension: the stronger the intermolecular forces, the higher the surface tension. Raising the temperature of a liquid will reduce its surface tension because you're providing energy to overcome that surface area, all right? You're increasing the temperature, you're increasing the kinetic energy, right? We know these two are proportional. That means the molecules are moving faster, which makes it easier for them to stretch and separate and overcome the intermolecular forces that hold them together. Surface tension is what is why we can take a paper clip and very gently put it on water, right? Even though steel is denser than water, if you do it very, very gently, you could try this experiment at home too. Try it very, very gently. You have to take a small enough paper clip that has a very minimal amount of surface area itself. And then if you put it on a water surface, that surface layer acts like elastic skin. It allows the paper clip to float even though it should sink. If you then tap it, give it enough energy, a movement energy, right? Give it enough kinetic energy, the paper clip will then fall, all right? Viscosity. Viscosity is the resistance of a liquid to flow. So it is in units of a poise. 1p is 1 gram per centimeter seconds, right? Notice that it's an amount per distance and unit of time, all right? Often given in centipoises, CP. So water at room temperature has a viscosity of 1 centipoise. The larger, again, intermolecular forces of attraction, the larger the viscosity, the harder it is for the liquid to flow, the more resistance it has. So just pulling out some basic hydrocarbons, these have dispersion forces only, right? So we're comparing like things. We're not comparing apples to kiwis. We're comparing apples to apples. When we increase the surface area, we have more intermolecular forces, right? Nonane down here at the bottom has a higher molar mass. It's a longer structure. So it would have a higher amount of intermolecular forces. And that's how we see the viscosity is 0.711 versus pentane, which is smaller, right? Less molar mass, smaller structure there, smaller surface area, smaller amount of intermolecular forces, less resistance to flow. Flows easier. Factors affecting viscosity, again, the stronger the intermolecular force of attraction, the higher the liquid's viscosity. The more spherical the molecular shape, the lower the viscosity. Why? Remember, the more spherical the molecular shape, the less surface-to-surface contact, the lower attractions, okay? And so again, this is all of the same kind of thing compounding on each other. Raising the temperature of the liquid, you're raising the average kinetic energy again, you're increasing molecular motion, you can overcome the viscosity. So just looking at the viscosity of water here at 20 degrees Celsius, it's around 1 centipoise. If we were to increase the temperature, increase the molecular movement, increase the kinetic energy, we're able to flow easier, 0.28, big drop off there. Capillary action is the ability of a liquid to flow up a thin tube against the influence of gravity. This is really helpful because that's how, plants get water from the ground and are able to transport them up into the leaves. It's the action against gravity, right? And so what does this have to do with intermolecular forces? Well, capillary action is the result of two forces working together, cohesion and adhesion. Okay, cohesive forces hold the liquid molecules together, such as water. Adhesive forces attract the outer liquid molecules to the surface of whatever they're riding up. We're going to choose things like tubes or cylinders, right? You can think of pouring water into a cup versus finding a graduated cylinder in your house if you got one of those, or just a smaller cylindrical holder, a smaller cylindrical cup, if you will, and noticing the differences. The adhesive forces are what pulls the surface liquid up the sides of the tube, and the cohesive forces pull them back to the middle of the liquid. And it's the balance between these two that creates a meniscus. Now, depending on what type of liquid you have, whether it's water, this is water over here, versus mercury. Okay, water has a meniscus that creeps up the side because the adhesive properties are more strong than the cohesive properties. Okay, the meniscus of water is what we call concave. All right, the adhesion to the glass is stronger than the cohesion to the water itself. Mercury, on the other hand, has a convex bubble right here, a convex meniscus where it bubbles up because the glass in the tube is not attracted to the mercury itself. So the adhesion is weaker than the cohesion. The cohesion with the mercury interacting with itself is much stronger than that of the actual glass itself. This is because metallic bonds are stronger than intermolecular forces. Metallic bonds is another type of covalent, somewhere between a covalent and an ionic. It's a chemical bond, all right? That chemical bond of metallic bonding is very, very interesting. We don't often study it in general chemistry, but that's what you can attribute this to. The mercury itself is interacting in a chemical bonding type of way rather than an intermolecular force type of way.